Hello, today we are going to talk about angular momentum algebra. Now, what is angular momentum algebra? So, word angular momentum is quite familiar from the classical physics as well, where we know if a particle of mass m, for example, is rotating in a circular motion or any kind of angular motion for that matter, with a linear momentum p equal to mv in this direction, and suppose this is rotating around this point. So this angular momentum L, if this is the origin and this position vector is R, so the angular momentum L vector is defined as R cross P in classical physics. In the same fashion, since electrons they revolve around a circular orbit around the nucleus, so the same concept of angular momentum is equally applicable in quantum mechanics as well. The only difference is that in quantum mechanics, these classical objects, these classical vector quantities are replaced by the corresponding operators. For example, if I write this relation in the quantum physics, so I would write something like this, where I put these hats on these L, R and P quantities, which signify that these quantities are nothing but the operators. And since they are observables, that means we can measure these quantities in experiments. They will be represented by Hermitian operators in quantum mechanics, because Hermitian operators have real eigenvalues. These eigenvalues are correspond to those experimental values which is obtained in the experiment to measure these quantities. Now, what's interesting about this angular momentum algebra is that this L operator or different components of this L operator follow a very interesting algebra, very interesting commutation relations among them, namely Lxy, Ly, Lz. The algebra is known as angular momentum algebra, and that is very useful in the study of different physical systems in quantum mechanics, in nuclear physics, in atomic molecular physics, etc. So we'll see how to reach to those relations, what are those relations, what are the importance of those relations, etc. Okay, let me start with, for example, if I take the x component of this relation here, it means if I take the, this is, since it is a vector, it has x component, y component and z component in 3 dimensions. Suppose this is my x, y and z. So any vector r in 3 dimensions will have 3 components along z axis and along x axis. We know that z equal to r cos theta, y equal to r sin theta, sin phi, and x equal to r sin theta cos phi. All these things we know. Symbols have usual meaning, where theta is the angle with the positive z axis, y is the angle with the positive x axis of the component of r along xy plane. All these things we know. Now let's try to see the relations between Lx, Ly, among Lx, Ly and Lz rather. We'll see the relations among Lx, Ly and Lz. These are the 3 different components of this angular momentum vector along the x-axis, y-axis and z-axis. Now let's see, if I take the x component of this relation, for example, that will read as Lx r cross p x component of this. And if we remember our vector product, this will be nothing but ypz minus zpy. It's cyclic in nature, x, y, p, z minus z, p, y. Similarly, if I talk about Ly, that will be z, p, x minus x, p, z. Similarly, Lz would be x, p, y minus y, p, x. Alright. So, if I, now in quantum mechanics, since these quantities y, z, p, z, x, px, py, lx, ly, all these are observables, all these are commutators. So I can, if I write this relation in quantum mechanics, so this will be written as this. The same classical expression that we had just written, this same quantum analog of the same relations is this. Now question is, now what is the commutator of Lx and Ly, for example? If I start asking this question, that what is the commutation relation between Lx and Ly. Before we find out this relation, it is important to note that the magnitude of L square, magnitude of the angular momentum L, the magnitude of the square of the angular momentum L square, that is equal to Lx square plus Ly square plus Lz square classically. In the same fashion, quantum mechanically also, this will be equal to different operators corresponding. Okay, and we also notice that L, which is actually equal to R cross P hat, this is an Hermitian operator. How do we know that? Because if I start, for example, I like Lx hat, and that will be I had just written ypz minus zpy in the operator notation. If I take the Lx hat dagger, what is the Hermitian operator? If I take the dagger of an operator, that is, if I take the Hermitian conjugate, first I take the complex conjugate, then transpose, then this will read as pz dagger y hat dagger minus py hat dagger z hat dagger. Now, since this operation of taking Hermitian conjugate, this flips the order, it changes the order. So pz dagger, y hat dagger, and py hat dagger, and z. Now, since yz and py pz, these are Hermitian operator. Linear momentum is a Hermitian operator because we know, for example, px is in minus ih cross del over del x, which is a Hermitian operator. If I take the Hermitian conjugate of this, if I take the Hermitian conjugate of this, for example, this will become minus ih, iota will be replaced by minus iota, this will become plus ih cross, and then del by del x, dagger of del by del x, which is minus del by del x. Okay, so it means it is a Hermitian operator. So this px, py, pz, these all are Hermitian operator because they are observables in quantum mechanics. We can measure them in experiments. Similarly, y and z are also Hermitian operators. So this dagger can be, since they are Hermitian operators, I can forget about these daggers. This will be equal to this. Okay. Now, which is what we get is Lx hat dagger is equal to pz hat y hat minus py hat z. Now, if we look carefully, this y hat is the position vector along y axis, position operator along y axis, and this pz hat is the z component of linear momentum. Similar, so these are totally in different direction. That means they don't talk to each other. They are simply independent operators. In a sense, they commute with each other. Similarly, py hat and z hat, they commute with each other. So I can write down this as this, which is nothing but the Lx hat. So it means Lx hat dagger is same as Lx hat. It means Lx hat is an Hermitian operator. Same is true for Lx y hat and Lz hat. Hence, we can conclude, since Lx, Ly, Lz components are Hermitian, so this L vector is also Hermitian. L operator is also Hermitian because L operator is nothing but y hat p z hat minus z hat py hat, or let me write down in this fashion. This is nothing but Lx hat operator I hat plus Ly operator j hat and Lz operator k hat. So since these components are Hermitian, these operators are Hermitians, so it means it is L hat operator is also a Hermitian operator. Okay, so that's the first thing that we conclude. Second thing is, we ask this question that what is the commutator of Lx hat and Ly hat. So let's try to find out the answer. Okay, so Lx hat, Ly hat is equal to ypz hat minus zpy hat because the x component is this and the y component is zpx minus xpz. Now we have to solve this commutator and find out the value of this commutator. Now let's do that. So we know a certain rule of commutator algebra that a hat plus b hat comma c hat plus d hat commutator is equal to a hat comma c hat plus d hat plus b hat comma c hat plus d hat, and then further we can write down. Similarly, we can further break this. And we also know that, for example, a hat comma b hat c hat is equal to b hat a hat comma c hat plus a hat comma b hat c hat. Okay, so we keeping these rules of commutator algebra in our mind, we'll solve this commutator. So what we get is the following: y hat pz hat comma z hat px hat minus x hat pz hat, this with this minus z hat px hat, this minus is due to this, z hat py hat comma z hat px hat minus x hat pz hat. Okay, which is equal to, now further we can apply the same rule, y hat pz hat comma z hat px hat minus y hat pz hat comma x hat pz hat minus z hat py hat comma z hat px hat plus, this minus minus makes plus, z hat py hat comma x hat pz hat. Now we'll apply the second rule of commutator, a hat comma b hat c hat is equal to a hat comma b hat c hat plus b hat a hat comma c hat. So that rule we will apply here. So we'll see here that when apply the same rule in the first bracket, that will become y hat pz hat comma z hat px hat plus y hat comma z hat px hat pz hat. Okay, this is the first bracket that I have written. Now if you see, so in the further next step, I take px hat this side and z hat in this side. So I am solving this separately. So when I solve this separately, I get y hat z hat from here, pz hat comma px hat plus y hat pz hat z hat px hat, and plus this is z hat y hat comma px hat pz hat plus y hat comma z hat px hat pz hat. Now if we see carefully, so these are the two components of linear momentum in different direction, so they will commute. This is 0, this is pz and px. Similarly, this is y component, this is x component, so they commute. This is 0. Similarly, y and z, they are two position vectors in different direction, so they also commute. What is left with? We are left with this thing, which is equal to y hat pz comma z hat is, we know from uncertainty principle that this is equal to minus of IH cross. So this is minus of IH cross px hat. So the first bracket gives us this non-zero value. So let me put this fashion. This first bracket here gives me minus of IH cross y hat px hat. This is the first. Now we come to the second. Now when we come to the second, we notice that if we apply the same rule here, so we'll see in the first step, we'll get y hat pz hat comma x hat pz hat. So pz will commute with both x hat and pz hat. Okay, so let me write down, let me solve the second bracket separately so that it is clear to you. X hat pz hat, that will be equal to y hat pz hat x hat pz hat plus y hat comma x hat pz hat pz hat. Okay, so in the next step, y hat x hat pz hat plus y hat pz hat comma x hat pz hat plus y hat x hat y hat pz hat, pz hat, and one more term which is plus y hat, x hat, and pz hat square. Now, again, if you look carefully, this is pz hat, commutator of pz hat with pz hat, which is 0. This is commutator of pz hat with x hat, which is also 0, because this is in z direction in momentum, this is in position in x direction. Similarly, y and pz is also 0, y and x are also 0. So this second bracket doesn't contribute anything in this expression. This is 0. Similarly, third bracket. So similarly, third bracket. So if you find out, so this will be, again we'll find out that this contribution is also 0, because if you do the same algebra here, so this will give me 0 again, because z hat with z hat commute, z hat with px hat commute, and py hat and px hat will also commute with each other. So this will also give me 0. However, here I'm expected to get a non-trivial value, because z hat and pz hat has a non-trivial commutator, while py hat and x hat will have trivial commutator, py hat and pz hat will also have a trivial commutator, but z hat with pz hat will have a non-trivial commutator. So let's find out this last commutator of this expression, which is x hat pz hat is equal to z hat x hat pz hat py hat plus z hat py hat comma x hat pz hat. Okay, so here this will give me 0, because py hat will commute with x hat also, py hat commute with pz hat also. So this will give me 0, while in this case I will have to solve it. X hat, z hat, pz hat, py hat plus z hat comma x hat pz hat py hat. Now again, this is the z component of the position vector, this is the x component, totally in different directions they will commute. This will give me 0. So what I'm left with, this is the non-zero value, because z hat and p hat has a commutation relation which is IH cross. So x hat and py hat. So the last bracket gave me non-zero value, which is this, and the first bracket gives me non-zero value, this. So overall, this left hand side that we asked that what this commutator is equal to, we have actually obtained the two expression minus IH cross y hat px hat from the first commutator, and from the last one, this is the value that we get, plus IH cross x hat py hat. Okay, so this gives me, if I take IH cross common, so this gives me x hat py hat minus y hat px hat, which is nothing but, what's this equal to? This equal to Lz hat. If you remember, the z component of L, because was, if you remember, we wrote down in the beginning itself that Lz hat, since L was r cross p, so the Lz component was xpy minus ypx. So that's exactly what we get. So this commutator here is Lx comma Ly, Lx comma Ly hat is actually equal to IH cross Lz hat. It means if we take a physical system and measure Lx hat and Ly hat, then it depends on the order, in which order we make the measurement. That is, if we take measurement of Ly hat first, then Lx hat, or in the second case when we take the same copy of the system and we take Lx hat first and then Ly hat later, so both will give us in general a different result. Okay, similarly we can prove that this is also equal to IH cross Ls hat, this relation holds this, and this z hat comma Lx hat is equal to IH cross Ly hat. So these are pretty cyclic in nature, and this set of commutator relationship define angular momentum algebra. Okay, which is the base of Lie algebra and other things, because angular momentum is closely related to the rotations, and this commutator of 2 rotation is another rotation. All these things are there, but for the time being we are focusing on this relation Let's go further and try to find out that what is the commutator of, for example, L square with Lx. So let's try to find out that also. Okay, so L square comma Lx hat is equal to L hat square is equal to Lx hat square plus Ly hat square plus Lz hat square comma Lx hat. If we solve this by commutator algebra, this is equal to this. So Lx hat square will commute with Lx, because in the last bracket we get Lz hat, Lx hat and Lz hat. Okay, so now Lx will commute with Lx, Lx will commute with Lx, these all are zeros, and similarly we see that that's it. Now you see Ly and Lx hat, commutator of these two is equal to IH cross, this is equal to IH cross Lz hat. Okay, sorry, minus IH cross, because commutator of Lx hat and Ly hat is IH cross Lz hat. So it's a reverse order, so put a minus here. Similarly here, minus IH cross Lz hat, Ly hat from this, and similarly from here we see this is IH cross Lz hat, Ly hat, and this is IH cross Ly hat and Lz hat. So this precisely cancels out this, and this precisely cancels out this. So this commutator is actually 0. Similarly, we see that this commutator is also 0, which is equal to L hat square comma Lz hat also. So by the same algebra. So this L hat square operator actually commutes with Lx, Ly and Lz. Okay. So these are the important commutator relations that we have to keep in mind. The further details of these relations and other importance and a few other relations we'll see in the next video.